Hi everyone, so today is lesson 4.7, applications involving exponential functions. There's a handout on Teams that you should print and fill out as you watch this video. So the top of the handout there says, there are several examples of real-life scenarios involving either exponential growth or decay. All of these examples involve three things: some sort of starting amount, A, either a growing or decaying factor, B, and a number of growth or decay periods, which is X. Therefore, the general form of the equation we'll consider today is y equals a times b to the power of x, where a was the starting amount, b is a growing or decaying factor, which is the base, and x is the number of growth or decay periods. Okay, so to determine the rate of growth or decay, first we're going to need to know if it's growth or decay. So if the base is greater than 1, it's going to be growth. And the growth rate calculation is growth rate equals b base minus 1 times 100, and that's going to be a percentage. Then if it's a decay, the base will be between 0 and 1. And the decay rate will be 1 minus b times 100%. All right, so let's do a few examples of that. So the examples say, determine the initial value and the rate of growth or decay. So the first one there, number 1, f of x equals 2 times 1.3 to the power of x. So the first thing we're going to ask, is this growth or decay? So is b, the base, greater than 1 or between 0 and 1? So the base here is 1.3, and that's greater than 1. So I know that this is going to be growth. So my initial value here is a, which is 2. And then I also need to determine the rate of growth. So if you look above the examples here in that little chart, remember we said the growth rate was b minus 1 times 100%. So here b is 1.3. So 1.3 minus 1 times 100% equals 0.3 times 100% equals 30%. So the growth rate is 30% for number 1. For number 2, f of x equals 100 times 1.03 to the power of x. First, we're going to look at the base to tell us if this is growth or decay. So the base is greater than 1, which means it's growth again, exponential growth. The initial amount, A, is 100. And now the growth rate, we're going to use the same formula as last time, b minus 1 times 100%. So b is 1.03 minus 1 equals, 0.03. Let's fix that. Times 100% equals 3% growth rate. Number 3. f of x equals 2,000 times 0.9 to the power of x. So our base here is 0.9, which is between 0 and 1, which means this is going to be exponential decay. Our initial amount is 2,000. And now our decay rate, we're going to use the other formula in the chart above, which is 1 minus b times 1,000. 100%. So B is 0.9, so 1 minus 0.9 equals 0.1 equals a 10% decay rate. All right, so next we have 3 common exponential applications, and these are going to be 3 that you will become familiar with and even possibly memorize. So the first one is compound interest. We're going to work down the columns here. So the equation for compound interest is A equals P times 1 plus I to the power of n. A is the final amount. So it stands for amount. It's the amount at the end. P is the principal or original amount. I is the interest rate per compounding period. So if your interest rate is 6%, but your interest compounds twice a year, then you would put in 3% because that would be half. Anyways, we'll get there. And n is the number of compounding periods. Okay, next one is exponential growth. Or doubling, because the number doubles each time. The equation here is A equals A0 times 2 to the power of T over D. A is the final amount again. A0 is the initial amount. And we use this expression because this is when time equals 0. That's where I'll write time. So at the beginning, when time hasn't started yet, your initial amount, this is how much you have. T is time, and D is the doubling period. And just a note here, T over D equals the number of growth periods. Right, exponential decay. Or half-life. The equation here is A equals A0 times 1/2 to the power of T over H. A is the final amount. A0 is the initial amount again, where time is 0. T is time, and H is half-life. And again, T over H is the number of half-life periods. All right, on to the examples. So we're going to use those 3 formulas from the chart to solve these 3 examples. So, number 1. $5,000 is invested for 5 years at 2% per annum, or per year, compounded monthly. What is the accumulated value? So this is a compound interest question, so we're going to be using the formula A equals P times 1 plus I to the power of n. Now, our principal amount, or the original amount that we start with, is $5,000. That's what we're investing, is the $5,000. Our interest rate is 2%. So that goes in a decimal form, 0.02 per year compounded monthly. So in 1 year, our interest rate is 2%, but we're going to be compounding it monthly. So now we need to see what our interest rate is each month. So we're going to divide this number by 12. And that leaves us with 0.001666, etc. Now, our number of compounding periods, n, is we are compounding this interest for 5 years, but we're compounding it every month. So 5 years times 12 months equals 60 compounding periods. Okay, so now that I have those three numbers, I'm going to plug them into my formula. So A equals 5,000 times 1 plus 0.0016 to the power of 60. All right, so when you put this into your calculator, 0.02 divided by 12, keep that number in there, and then add 1 to it here, and then leave that number in your calculator and do to the power of 60, which will be about 1.105. Leave those decimals in your calculator. Times by 5,000 equals 5,525.39. So therefore, the accumulated value is $5,525.39. All right, number 2. A bacterium divides into 2 every 3 days. There are initially 17 bacteria. How many will there be in 2 weeks? So this is exponential growth because they're dividing in 2. So we're getting more and more and more. So the formula for that is A equals A0 times 2 to the power of T over D. So the initial amount, A0, we start with 17 bacteria. Then we need time. So the question asks, how many will there be in 2 weeks? So time is 2 weeks. And then we need D, which is the bacteria divides into 2, so it doubles every 3 days. Now, we need D and T to be in the same units. Okay, so that means we either need to make this into weeks or this into days. It makes more sense to put 2 weeks into days. So 2 weeks is the same as 14 days. And then D is still 3 days. Okay, so now I have A0, I have T, and I have D. I'm going to plug those numbers in. So A0 is 17 times 2 to the power of 14 over 3. It's important to note, this is for the last one too actually, that only the 2 is to the power of 14 over 3, not the 17. So it's 2 to the power of 14 over 3 times 17. If it was also the 17 would be in brackets as well. So I have 17 times 2 to the power of 14 over 3. 2 to the power of 14 over 3 is approximately 25.398. Again, type this into your calculator, leave it in, and then multiply by 17, and you should get 431.77. So there will be 431 bacteria after 2 weeks. All right, number 3. 12 grams of trittium decays to 9.25 grams in 2.5 years. Determine the half-life of trittium. So this is exponential decay. So the formula for that is A equals A0 times 1/2 to the power of T over H. So let's see what we know. We have 12 grams. That's our initial amount. it decays to 9.25 grams. So that's what we have as an end result, which is our final amount. So this time we have A, which we haven't had yet. So A is 9.25. Then we have, how long does that take to happen? That takes 2.5 years, so that's our time. And what we don't have is H, and that's what we need to find. So let's fill in what we know, and then see if we can solve this. So we have 9.25 equals 12 times 1/2 to the power of 2.5 over H. Okay, so how could we find H? Well, we could use trial and error, but there's an easier way that I'm going to teach you. So before I get to the H, first I'm going to get rid of this 12 by dividing both sides by 12. So now I have 9.25 divided by 12 equals 1/2 to the power of 2.5 over H. Okay, so now what I'm going to do, I'm going to use logarithms, and we're going to take the logarithm of both sides. So we haven't learned this yet. This is, logarithms are the inverse of exponential functions, and we'll get to them, but for now, basically all you need to know is that logarithms are a button on your calculator that can help you when you're trying to find missing exponents. Okay, so what that means is I'm going to write log 9.25 over 12 equals log 1/2 to the power of 2.5 over H. So I can take the logarithm of both sides. It's like multiplying both sides by 5. What I do to one side, I have to do to the other side, and I'm allowed to do that because I'm doing it to both sides of the equation. I'm keeping it balanced. So I'm taking the logarithm of both sides. So what that allows me to do is, taking the logarithm allows me to grab this exponent and bring it down in front here. So now I have log 9.25 over 12 equals 2.5 over H log 1/2. So because of this logarithm, that's the only reason I'm allowed to do that, is now I have brought the exponent down to the front, and now it's multiplied. This is multiplication, multiplied by log 1/2. All right, so my goal is to get H by itself. So first I'm going to multiply both sides by H, so I can get it off being the denominator. Now these H's will cancel out, and I'm left with H log 9.25 over 12 equals 2.5 log 1/2. Now I want to get H by itself, so I'm going to divide both sides by log 9.25 over 12, log 9.25 over 12. Now this will cancel out, and I will be left with H equals 2.5 log 1/2 divided by log 9.25 over 12. Now, you're going to plug this into your calculator, this whole thing, and you will get 6.66 approximately. So, what does that mean? Well, that means that the half-life of trittium is approximately, well, exactly 6 2/3 years. Okay, so if you find the logarithms too confusing, which I can see that you might, because I'm not there to show you how to do it and you haven't heard of it before and it just all sounds confusing. If you find it too confusing, feel free to just use trial and error. Just plug in numbers until you get one that works, that makes the equation work. You can also just look up logarithms on YouTube and see what else you can find. Or Just message me if you have any questions, and I will try to help you as best as I can. All right, so have a good day, and I'll talk to you soon.